Hello, statistics class. In this first example, we're going to actually look at a problem that needs to be re-expressed. So we're going to apply some re-expressions and see what happens. So this is a chemistry example. It says Boyle's law. Oh, and before we get into this, if you were gone from class on Wednesday because of the photography trip or whatever other reason, you definitely want to very carefully look at the key provided for the Chapter 9 reading guide. We just spent quite a bit of time in class discussing that. There's some extremely important issues in there, probably one of the most important reading guides of the year, especially those ideas concerning separating out clusters of data within a scatter plot when there's more than one group of data combined and you have some reason to suggest that there's more than one group, how you need to create separate regression models for those groups if that's the case. And that really applies to an assignment that I just gave you. Hint, hint. Alright, so let's look at this Boyle's law problem. It says if you've taken a chemistry class, you're familiar with Boyle's law. I definitely think that's true, which is PV, or pressure times volume, equals some constant. So we have students in a chemistry class. They're doing a lab. They've got a pressure probe or a pressure sensor, and they've collected this data. So we're going to enter that data in our calculator and see what it looks like. You want us to describe it. So probably want to do the 3-feature description. So I've got a calculator I borrowed from somewhere over here. So I'm going to go to Stat, Edit, and start entering my data. Let's see, 6, 8, 10, 12, 14, 16, 18, 20, 2.9, 589, 2.4073, 1.9905, etc. I'll shut up now. You want to follow along with me if you aren't already. I think I may have one that's wrong here. Yep, 1.349. Okay, so I want to scatter plot that. So go to my plot, turn it on, scatter plot list 1, list 2, looks good. And zoom 9. Okay, there's my scatter plot. So I guess I could take a picture of that maybe and put it over here. We can go back to it if we need it. It says to describe what we see in the scatter plot. So let's come over here and describe it a little bit. I'll just keep my font like that. Okay, so what do you see? Remember, you want to, whenever you're describing a scatter plot or bivariate data, do the 3-feature description. So I'm going to do a complete sentence that says the relationship between pressure, and which one do we put as our x variable? I think we used volume, right? So I'm going to say between volume and just say x because that's the explanatory variable for this case. So the relationship between it and pressure, which we stuck as our y variable, our response variable, is, it looks like a pretty strong pattern. It is very strong, non-linear. This is clearly curved, right? I don't think it's that hard to see the curvature in that scatter plot. And I guess if it's not a linear relationship, direction is kind of a little bit nonsensical, but you can see it's kind of like exponential decay. So I'm going to say negative because of the decay factor. So whether or not you detect if a set of data is curved, once you detect it's curved, if you're going to study it with regression techniques, then you either need to apply a different regression model or do one of these re-expressions like we're going to be working with in this chapter 10 for the next week. So we've got something that's clearly curved. Let's say it was not quite so clear that the curvature existed, you could of course check the residual plot. I'm guessing we have a pattern in the residual plot. Let's create it though. So let's go and create our model. So I'm going to go to calculate linear regression model. Alright, there it is. It doesn't say what R is. You know what? I'm going to turn that on. Mode. Statistical diagnostics on. There we go. Calculate my model again. There we go. Yeah, very strong model, you can see. So let's go and create the residual plot. So I have the thing up there. Let's put the regression model right here. So I'm going to load it in here. You could do it by hand. I'm going to do it the fancy way. Variables, statistics, regression equation. There it is. So I'm going to now quit. I could put it on my scatter plot. Watch this. Now you can even really see the curvature even more. And you can kind of see what the residuals look like if you kind of think about grabbing this with your hand and pulling it down, this line down this way and tilting the whole axis by like 45 degrees, rotating the axis. But let's create the actual residual plot. So I'm going to go back to my lists, and in list 3, I'm going to say my actual y. Remember, residuals are actual minus predicted. So I'm going to go my actual, which is all the y's which are in list 2. So second list 2 minus the predicted y's, which I put the model in y1. So I'm going to go grab the model, and I'm going to plug in the x's into my model. Those are in list 1. So this says actual, the real y's, and I'm subtracting y hat. This is the model y hat where the x's are being plugged in. So there's my residuals. If I want to look at the scatter plot of that, go back to my scatter plot and plot x, or y really. You can do residuals with y as well, but I want to look at x versus the spacing or the residuals. Resume. Oh, let's quit. Zoom 9. And there you can see the residual plot for this data. Again, a very, very clear pattern. Why is that? Remember, when we go back to the original scatter plot, which I'm going to do now, the original scatter plot was very, very strong. In fact, it's so strong because, remember, we're plotting data that students collected. They measured it. But it's data that comes from Boyle's law, a physical law. So if they had measured it perfectly, if they had perfect instruments from like some sort of deity that provided them with perfect instruments and perfect no human error, then this would have been a 100% relationship. But it's clearly curved, and that's the point for today. So let's focus on that. So it says if the true relationship between the pressure and volume is this, like we said from the physical law, we can divide both sides to obtain something with a division. So that's the kind of re-expression that we really want to pursue. It's not real hard to figure out. Since we have a little bit of background knowledge about chemistry in this case from Boyle's law, we kind of know what re-expression to apply. You're going to be experimenting with different re-expressions on the couple problems for this weekend and on the majority of the other problems assigned next week. So apparently there's two transformations here. B says use the graphs to identify which transformations were used. So we're just supposed to identify the transformations that were used here. In the first graph, let's make the font smaller, the axes tell you. It says pressure has been left alone, it's measured in atmospheres, and they've gone 1 divided by the volume. So remember, pressure is y, so I'm going to say what the model is here is, let's move this to the left, is P equals, and then we've got our model, so let's go back out. Oh, well, we don't really know what our model is yet, right? So here we're going to have P equals, and I'll just say mx plus b, except it's not just regular old x, it's V for volume, and it's not just regular volume. They've taken the volume and gone 1 divided by the volume. So it's times 1 divided by the volume. Let's scoot that up a little bit. There you go. So that's the model that they were looking for. That's the first re-expression choice, transformation number 1. For transformation number 2, you can see that it looks like they tried 1 divided by the pressure and left the volume alone. Sometimes they'll do both. In this case, they just tried changing the y's, the reciprocaling the y's, and reciprocaling the x's separately. So this one has 1 divided by pressure equals m times regular volume plus some y-intercept. And of course, we could get what these m's and b's are if we go back over here to our model and calculate them. So remember, these would be these numbers right here. All right, let's continue. So it says, here is Minitab output. Minitab is a software program instead of a TI-84 for the separate regression analyses of the above transformations. 1 over volume for the x versus y, and volume left alone where you take the reciprocal of the y's. So we've got the actual, all this stuff that we've been seeing, the computer output from Minitab, the software program, and we've also got the scatterplots, the residual plots for those transformations after they've been applied already. So this one you can clearly see as a pattern, right? Don't we have a pattern going up and down like this? So this residual plot shows that going 1 over volume is an inappropriate or bad re-expression of the data. If you look at the second residual plot, you can see it's pretty randomly scattered. In fact, very randomly scattered. They're kind of all over the place. Yeah, maybe there's like a little bit of a W shape, but this is a pretty good random scattering. That's what you want to see. There's no fan shape where it's kind of like going out in both directions. You have small differences, small residuals that then become consistently large residuals. So you don't need to worry about that. It's fairly randomly distributed. So this 1 over y transformation is the way to go. So it says give the least squares regression line the appropriate one. We're going to pick this one. So remember, the idea was here that we had 1 divided by pressure equals the slope, whatever that is, times the volume plus the y-intercept. So where is that slope and y-intercept? Well, they've performed the calculations with Minitab, the software program, already for us. We don't know what t and p is yet. That's next semester. Standard error of the coefficient, I don't think we even use much next semester, maybe once in a while. Predictor, constant, volume. Constant and volume are kind of things that I recognize, and coefficient is a word I know about. So constant must mean the y-intercept, so this must be this number right here, 0.100170. And volume is the x variable for this model, right there, you can see it. So that must be the coefficient means the slope. So that's 0.0398119. So there's our new regression model. Define any variables. I guess if we're doing this the right way, then we'd go like this, right? We'd say pressure hat. So let's see if we have a symbol in Microsoft Word for hat. Surprise, surprise, we do. So pressure hat, and let's type in all volume here. That's the way we've been making regression models look in our class, right? So there you go. There's our regression model. Let's see what predictions they want us to use it for. It says predict the pressure in the syringe when the volume is 17 cubic centimeters. So that means we've got 1 divided by P equals 0.0398119 times 17 is the volume plus 0.100170. This is all just a number over here, so I just need to type that in my calculator. Let's clear this out and come over here and say 0.003988119 times 17 plus. So I got 0.16. So we have 1 divided by pressure, not pressure, equals 0.16785023. And I'm being very careful and not rounding on this problem because these are physical laws, and I want to try to use as much precision as possible. So now to solve this, of course, you multiply by p on both sides. So I take this p, multiply on the left by p, multiply on the right by p. I get this, then I need to divide 1 by 0.16. So we get P equals, well, I'll just say approximately 1 divided by 0.16. If I actually do that fully on the calculator over here, 1 divided by 0.16785.023. So that pressure is going to be 5.957693229 atmospheres. So that's the units of pressure that we're working with here. There's all kinds of other units of pressure that you use. Pascal is the actual SI unit, but let's not get too chemistry/physics-y today. All right, E says predict the volume of the liquid when the pressure is at 2. So now we've got 1 divided by 2 atmospheres equals 0.003819 times the volume, which we don't know, plus 0.1. And we need to solve for V. So first I'm going to subtract this, of course. So I'll have 0.5 minus 0.00. Oh, oops. 0.5 minus 0.100170. All right. Type that down here. And we've got this coefficient on V, our slope thing left. So we're going to get V equals what? Well, we take that and divide by 0.003. So that is a volume of 100.429771. And what was the volume unit? I don't remember what it was. Ah, it's always on your graph right there, or if we go all the way back up, it's clearly right here. Cubic centimeters. So centimeters cubed. All right, so that's what we'd predict for 2 atmospheres. So now it says predict the pressure when the volume is 1 atmosphere. So we could go ahead and just stick that in. But every time you're asked to make a prediction with a regression model, I'd always think about, is that really a legitimate thing to do? So let's go back up and look at our table and come back down here. So this is the original data that we had, right? We knew about volumes for 6 cubic centimeters up through 20. We knew about pressures between about, 3 and 1. It looks like 1 to 3. So down here when they asked us to make a prediction for 17 cubic centimeters, 17 is in our range of data. In fact, let's just go back to over here. We can look at it in our lists at the same time. So 17 was in our range of data, so this was a legit prediction in part D. In part E, they asked us about 2 atmospheres. Well, 2 atmospheres was in our pressure data, so that was also a legitimate prediction to ask us to do. When they ask us to do a volume of 1 centimeter cubed, that's an x of 1. X of 1 is pretty far outside below the range of values here. So we could try that, but something about the situation might change dramatically, I think. That's not really a valid prediction. So I wouldn't, this is what I would say, I wouldn't want to make such a prediction because 1 cubic centimeter is decently far outside my range of data used to construct my original model and also my 1 over y re-expressed model. Hence, this is a dangerous extrapolation. There you go. So there's an example of re-expression using reciprocals. Now you want to move on and watch the other lady's video about the most common, probably, re-expression, which is logarithms, either logarithming the x, logarithming the y, or logarithming both. Those are extremely useful re-expressions. I'll see you next time. So one last comment before I move on. If some of you were more awake than I was this morning, hopefully you caught a mistake I made, just a little tiny decimal mistake that I made, which I should have caught myself. Luckily I have my cat here with me, and he managed to catch it. So if you hear the purring in the background, yeah, that's because my cat's feeling lonely right now. So, where's my mistake? So, I should have caught this a second ago while I was doing it, but I was focusing on explaining or something. I don't know. Maybe I just lacked cat intuition. So, I have a pressure here that ended up being about 6 atmospheres for 17 cubic centimeters. Let's go back to our original data and see if that makes it all sense. You should always kind of do that when you make predictions. So, I don't know why I didn't this time until a second afterwards. But 17 centimeters looks like it should be like 1 something, right? Like that was a really strong relationship, so it should be like 1.3, 1.2, you know what I'm saying? Well, I got 6. So where is my mistake? Well, a second ago I fixed it, but a second ago I put an extra 0 here. You see? Extra 0. Yeah. And here as well. So it made both of these come out unrealistically. Let's see if my prediction in E was correct. 100 cubic centimeters for 2 atmospheres. Go back and look. 2 atmospheres is like here-ish. That should be like 9, 10, something like that. Not 100. Come on. Both of these are completely unrealistic predictions. So this really shows the point of checking to make sure your predictions are realistic based on the data that you've collected. So here's where I fixed that mistake and cut out that extra 0, reperformed the calculations, and I got about 1.28 atmospheres for 17 cubic centimeters. And for 2 atmospheres right here, I ended up getting 10 cubic centimeters, which it makes sense based on what we looked at a second ago. All right, now that we're good, Kitty, I think we'll sign off. All right, say bye.